that if you did the first test and you were actually trying to go back and look at your notes, now you should have a lot more concise notes to maybe find stuff to help you. But second semester we talked about integration. Remember that we started by using Riemann sums, LRAM, RRAM, MRAM. The AP test uses left Riemann sum, right Riemann sum, midpoint Riemann sum. I don't think they usually use LRAM, RRAM. I don't really remember. I don't think they do. But remember, it's just where you break it up. And we've seen a lot of times on the free response, there are even some on the multiple choice. If they don't want the exact answer, they want the approximation using the appropriate sum to do that. And so remember that area of a rectangle is just length times width. So we find the length of the interval. Your book always gives this lovely formula. If you take the b minus a divided by the number of rectangles, that'll always give you your width. Most of the time, we just kind of figure it out. If I'm from 0 to 2, and I want 4 rectangles, I can figure out how wide each one of those are. And then the height is always the function's height there, depending on whether it's the left, the midpoint, or the right. That's what you're plugging back in there. And we've done one like this on the last test on the free response. Is it underestimating or overestimating? It depends on if the function's increasing or decreasing, and it depends on which one you are, left, right, Riemann sum. And so you always just want to kind of look at it and think about, I always just draw the rectangles in to do that. So I just have this lovely trig one, because I always like doing trig. So approximate the area beneath g of x equals negative cosine of x from pi halves to 3 pi halves using 4 subintervals, using left sums and right sums. So when we're approximating area, right, that means we're approximating the integral of pi halves to 3 pi halves. But instead of actually integrating it, we're going to approximate it using rectangles. We can also approximate it using the trapezoid rule formula if asked for that. So what's going to be the length of my, this one's a little bit trickier maybe. If I go from pi halves to 3 pi halves and I want 4 subintervals, what's halfway between pi halves and 3 pi halves? Because this will be pi, right? Halfway in between. So then halfway between that would be 3 pi fourths and 5 pi fourths. So yeah, I think our width, this is one where the width is going to be the same. Remember that a lot of times on the free response, they give you the chart or they give you the graph, and each rectangle is a different width, so you might have to set up each one. If they're all the same, we could just put that width out front, and we could say pi fourths. And then if I'm using left sum, right, a left Riemann sum, I'm going to use the left endpoint of each one. So I'm going to start with pi halves. I'm just going to kind of show my work here. I'm going to say g of pi halves plus the second rectangle would be 3 pi fourths to pi, but I'm using the left endpoint, so that would be g of 3 pi fourths. And then the next rectangle would be pi to 5 pi fourths, would be pi. And then 5 pi fourths to 3 pi halves would be a height at 5 pi fourths. And remember, there's 4 rectangles, so I should have 4 heights there. I always remember with the left Riemann sum, I'm not going to use the last endpoint. And with the right Riemann sum, I'm going to skip the first one and use the second one. They're never going to give you one of these on a calculator because they know that there's programs for Riemann sums, and they want you to do them by hand. So they're not going to be terrible math, but they're going to be wanting you to do this. So remember, on a no calculator, you don't actually have to add it all up, but you do have to actually plug this in here. And if I plugged pi halves in there, you can't just leave it as cosine of pi halves. That wouldn't give you the points either. You have to evaluate it. So I'm going to just do this. Cosine of pi halves is just 0. Do you agree with that? Plus, what is the cosine of 3 pi fourths? Over there, right? Negative square root 2 over 2, but there's a negative in front of that, so that's going to be positive square root of 2 over 2. Plus, at pi, cosine of pi is negative 1, but again, the negative in front makes that a positive 1. And 5 pi force is also negative square root of 2 over 2, put a negative in front, makes it positive square root of 2 over 2. And on a no calculator free response question, you definitely could leave your answer like that. If it was multiple choice, you'd have to work it out. But remember, on free response, you can leave it like that. But it's really not that bad. It should work out if it wasn't free response. That would just be square root of 2 plus 1. Is that true? The square root of 2 over 2 plus square root of 2 over 2 is 2 square root of 2 over 2. 2's cancel out. I don't know. I don't think it really gets much better than that. This would be my left approximation method. What would I have to do for the right one? Do I need to redo all this work? My width is still the same, but I'm just going to skip this one, right? And I'm going to need cosine of 3 pi halves. What's cool about cosine is what's the cosine of 3 pi halves and the cosine of pi halves? They're the same. They're both 0, which means I think that our LRAM and our right RAM are exactly the same on this. I will tell you on free response, they always give you a point for showing the sum. So you want to make sure that you show every Riemann sum. But you would actually do like G of 3 pi force plus G of pi plus G of 5 pi force plus G of 3 pi halves. But I'm just going to say it's the same answer. I've never seen a question where they ask you to do both. I just wanted to go through it. And again, remember, a lot of times they're not equal width, and you have to be We also learned that more accurately, we can use trapezoids, because trapezoids have less space there. There's this lovely formula that we derived. I don't know how much you remember this or not, but because the area of a trapezoid is 1/2, that's where the 2 on the bottom comes into play. The width or the height of each rectangle, b minus a over n, that's just the, that height on the x-axis that we do. And then it's the sum of the bases, and the bases are the functions. And so remember that all the trapezoids share a side with the one next to it, so that's why we double all the ones on the inside and not the ones on the outside. Here's what's really great. You don't have to memorize this because you could just do each trapezoid separately, right? Like the area of a trapezoid is 1/2 times the height times base 1 plus base 2. So if you don't think you're going to memorize this formula, just do this. And most of the time, not always, but most of the time on the free response at least, it's just like the Riemann sums. They're not equal heights anyway, so you can't use this formula because some have a height of 10 and some have a height of 30. So you actually have to break it up into individual trapezoids anyway. And so don't feel super stressed about memorizing that because this formula will always work to do that. And again, you could always draw it in to see whether it's overestimating or underestimating. But unlike Riemann sums, you don't have to think about, well, it's different for left and right, and it's different whether it's increasing or decreasing. For trapezoids, if it's concave up, it's going to overestimate the area. If it's concave down, the trapezoid is going to be underneath it, it's going to underestimate it. So to me, that one's easy for me to remember, but you could always just draw in a trapezoid. There's lovely questions. I don't remember on this test or not. I've taken so many in my life. But they give you graphs and ask, like, which one does a trapezoid overestimate and a left Riemann underestimate, or stuff like that. So I picked trig for us. Approximate the area using trapezoidal rule with 4 trapezoids. And again, I picked even ones, which means we could use this formula, but we could also, I feel like we're not going to use the formula most of the time. You could just break this up. Like this would be pi halves, and then this would be pi force and 3 pi force. So you can see that on this one, each of the widths is pi force. So if you didn't know that, or if they were different, you just take each one. So you can take 1/2 times pi force, that's the width, And then the sum of the bases are going to be what are the y values at these points, right? So that's going to be, I don't have it written as f of x, but it's going to be like f of 0 plus f of 5 fourths. Or you could just go ahead and say sine of 0 plus sine of 5 fourths. And you can do that for each trapezoid, and it's always going to work. You're going to see it's really easy to derive this formula when we write it all out, because the 1/2 you can factor out for everyone. The pi fourths, that's the v minus a over n, you can factor out all of them. And you're going to see that these middle ones, it's going to repeat itself, and so that's why. So then I can say plus 1/2 times pi fourths times f of pi fourths plus f of pi halves. Second trapezoid. And the third is going to be f of pi halves plus f of 3 pi fourths. Again, you can see, right, that's repeating itself. That's where the 2 comes in. So pi halves and pi halves, it's sharing a base. But the first one and the last one do not share a base because they're the outside edges, so that's why they don't get a type 2. Why not take straight? Alright, so what's that? Pi 8. Sine of 0 is 0 plus radical 2 over 2. Square root of 2 over 2 plus 1. Um, 1 plus square root of 2 over 2, because remember sine is positive in quadrant 2. What's really great is if this was on a no calculator part of a free response, right, I could leave this big ugly answer and I don't have to, right, like this is an acceptable answer and I don't have to do any more because I have all numbers here now that I could leave that. I've seen where, I don't know if we've had this one yet or not either, but they give you a table and they said the trapezoid approximation was this much, and they asked you to go back and find a missing value from the table. And so this way would work on it. It's where maybe the original formula with the 2's is a little bit easier to do on that. Other than that, I don't think I've ever felt like that the actual formula was more helpful. And on the free response, almost always those widths aren't the same, so you have to break it up. Okay? Okay. So remember that you just have to be able to integrate on the no calculator part. Some are going to be kind of easy, but there's definitely going to be substitution. There's definitely going to be, after your bounds with substitution, there's definitely going to be, making sure you pay attention what's happening there. Remember, if there's no bounds, we put the plus C. There's a lot of times where you have to do the plus C and then solve for C and go back on the multiple choice. We'll look at a lot of those. And remember, there is no product or chain rule or quotient rule. You have to use substitution, or there has to be a rule for it. LN's going to show up a lot on here as well, kind of recognizing it. Inverse trig, like I said before, the only inverse trig I've ever seen is inverse tangent, because it's really easily mixed up with ln, because remember it's 1 over x squared plus a squared. So that's the one that I've seen on there the most. But just try this if you haven't already. Some good old integration. I just 3 wrote line, just to kind of remind you, right? The 3 on the bottom, that's just a fraction you can pull out front. Anytime you have a radical, you can write it as an exponent, so you can do that power rule where the integral of x to the n is just x to the n plus 1 over n plus 1, or base rule. So this would be 2x to the 5th over 5 plus 1/3 x to the 4th over 4, or maybe you went ahead and changed that to 1/12. And then if I add 1 to 1/2, that would be x to the 3/2. And remember, dividing by 3/2, hopefully we're in the habit now that we can just flip that over as reciprocal in front. And so obviously I would change this here. Lots of applications with that, of being able to integrate and then use an initial value and solve for C and do a whole bunch of stuff with that. So as you look through my workout solutions, you're going to see a lot of things where I write FTC part 1, FTC part 2 for fundamental theorem of calculus. And we'll see if maybe we can get through this first slide here, and then we'll probably come to tomorrow there. But fundamental theorem of calculus has 2 parts to it. And the first part tells us that what we know, like what we know way before we got to this theorem, is that the integral gives us the exact area under the curve. Part 1 says that if you take the integral of this, and I don't know why I changed this to g's, I think because I was using that Idiot's Guide to Calculus. When we did this, we called this capital F of x, and if you want to change this to capital F of x, you can. But it just says if g of x is the antiderivative, or we could say capital F of x is the antiderivative of the continuous function f of x, then when you take the integral from a to b of that you just get capital F of b minus capital F. The antiderivative, you plug it in, and it gives you the exact area. No need for rectangles, no need for trapezoids, no need for a front calculator. That's how we take the exact area. 2 important properties of this that we've seen on some free response questions already is that if you take the integral from a to a, there is no area, right? That's just a point. So anytime they ask you to take an integral from a point to the same point, it's just 0. That has shown up on like part A of a free response before. And then this one that we used the other day when we went through one is that if you switch the bounds, right, if it's in the wrong order, then you can switch the bounds and pull the negative out front. And obviously I had it as the right and then I switched it. So we don't need to do that. But if you switch the bounds, then you pull the negative out. We have to come on so good going. Part 2 is the part that that kind of confuses people sometimes. But part 2 basically says that when you take the derivative of an integral, then it kind of cancels it out. But really tricky is if you take the derivative of an integral from a to a function, which a lot of times we think of that as just a to x, right? Really easy. Here, I'll write the easier one. You take the derivative of the integral of a to x of g of y dy. Then we know we just put that x in there, and that just becomes g of x. I wrote it out as if, what if it's something other than x up there? If it's some other function, you have to kind of do the chain rule of the derivative kind of cancels the integral out, so you can just plug in f of x into your g function, just like I did here. But then you have to multiply by what the derivative of this is up there. And that's what I guarantee you're going to see. If you go back through the test you took already, I guarantee there's at least one multiple choice question that they ask you to do something like this. And people miss it all the time. 1, because they just kind of get thrown off by the derivative and the integral in the same parts. And 2, they forget to multiply by the derivative of that upper bound. So when you evaluate this, it doesn't matter what the number on the bottom is. If it's a number to a function, you're going to put that function in there, the derivative of the integral. That's just going to be e to the tangent of x then you have to multiply by the derivative of that function. The derivative of x is just 1, so that's why this is just g of x. But the derivative of tangent x is secant squared. No plus c, because we took the derivative of the integral. So if you see on my multiple choice on a question, FTC, that's what I'm doing here. And then that leads us to those types of questions that was on the previous class we went over last week, and also maybe a little bit like today, maybe, where they ask you to evaluate a function when the function equals the integral. So like this one, and the x is just like, find f of 4 if f of x equals this. Well, if I replace x with 4, right, that just becomes an integral that I can evaluate. So if they ask you to evaluate a function that equals an integral and x is at the top, all you're doing is replacing x with that number, and now you can do, this is fundamental theorem of calculus part 1. You're just integrating it, and you're going to do capital F of B minus capital F of A. So that would be t squared over 2 minus 4t evaluated from 4. So that would be 16 over 2 is 8 minus 16 minus 4 over 2 is 2 minus 8. Is that just negative 2? Am I doing my math right? Because that's going to be plus 8, and then that's going to cancel out this negative 16. So that's going to be negative 2. Oh, there you go. So I'm supposed to say x. So this is what shows up on the free response questions a lot. Sometimes it's with the graph, like the ones that we've done, and sometimes they just ask you these questions. If g of x equals the integral from negative pi to x over 2, of cosine of 2t dt, g of 4 pi is just like this. We're just going to replace this x up here with 4 pi, and then it would just do fundamental theorem of calculus. I'm going to not work all the way out. I'm going to do that. But if I put 4 pi over there, 4 pi over 2, that would just be 2 pi. Is that true? Be careful when you integrate that, because it is kind of a u substitution, right, with the 2 there. But that's just an integration problem. But what happens now when they ask me to find g prime of 4 pi? Start with g prime next. When I take the derivative of the integral, that's fundamental theorem of calculus part 2, of that this is just going to go in here, right? Like it's going to cancel out the integral. That's going to give me cosine of just x. Is that true? But be really careful, because that's not just x up there, it's x over 2. So do I need to multiply by 1/2 as well? Well, also, I'm just going to put 1/2 in front here so I don't get confused. So not integrating it, taking the derivative of the integral, fundamental theorem of calculus part 2. Now, I can plug my 4 pi in there. And I would just get 1/2. And cosine of 4 pi is just 1, right? So the answer there is just 1/2. Here's the plan. Tomorrow, I'm going to go over that free response with you. Get back to you so you can see what you got on it. I have another day review, but I'm also going to give you a take-home exam tomorrow. And I don't know. We'll see. I really would like to do Friday, but I might even just be like the week on Monday. I mean, that's what I've done. But my advice is, no matter what it's due, don't put it off to the last minute. Like, what's smart to do would be try to do a section at a time, or at least half of a section at a time, if it's like 55 minutes, you don't have much time. Spend like 30 minutes a night on it, so that you can actually spend time getting it all done. And hopefully, if you get to even for yourself last time, you're going to get a lot better score this time. And as we go through the multiple choice, if you look through the multiple choice tonight, that's your homework tonight really, is look through my workout solutions with your solutions and see if you can get some things in there that maybe you didn't ever do. So questions, that's going to be Thursday if you go through that. So don't forget. I promise I bought these. I still am missing test corrections, Joey test corrections, Jacob test corrections, Adam test corrections from chapter 7 before spring break, it's all kinds of stuff. But just whenever. This week would be nice. I'll see you in
Naked Rogers, Noah Watson, Caitlin Sousa, Jacob Williams, and Bailey Sanders.